Close your eyes and imagine a world not as we know it today, with oceans separating distant lands and planes flying for hours to cross continents, but a world in which almost all the land was connected, locked together in one vast, unimaginable supercontinent. This was Pangea, a name derived from the Greek words pan-all and Gea earth, meaning quite literally all the earth. Around 335 million years ago, the restless forces beneath the crust of our planet gradually drew the scattered fragments of ancient continents together until they finally collided and fused. The result was a single, enormous landmass that stretched from pole to pole. Supercontinent, unlike anything that exists today. Pangea stood surrounded by a single vast global ocean, known as Panthalassa. Imagine the immense expanse of water. Waves endlessly rolling, stretching beyond the horizon, wrapping around the planet in blue immensity. The world during Pangea was not just geologically different, but also biologically and climatically unique. Plants, animals, and ecosystems had to adapt to an Earth shaped by a singular geography. A place where deserts were vast, mountains towered from fresh collisions, and coastal lines were far rarer than in the modern world of fragmented continents. Us today, continents feel permanent, almost immovable. Yet deep beneath the Earth's crust, the mantle churns slowly, pushing plates along like rafts adrift on molten currents. Over millions of years, continents drift together and apart in a cycle of supercontinents. Pangea was only one chapter. Of this grand cycle before it, there had been others, such as Rodinia and Gondwana. After it, the continents broke apart to form the familiar world map of our era. But it is Pangea that holds a special fascination, both because of its relative closeness in time compared to older supercontinents, and because it was the stage on which many evolutionary dramas unfolded, leading eventually to the rise of the dinosaurs and much later US. As we begin our journey through this ancient landscape, we'll travel section by section into the life, climate, and mysteries of Earth during the age of Pangea. Each part of this story is a glimpse into a world alien, yet strangely familiar. A reminder of the deep time our planet has endured. Pangea's story is not only about land and ocean, but also about life itself. During its reign, amphibians flourished. Reptiles diversified and forests spread across vast interiors. The Carboniferous swamps, rich with giant ferns and towering lycophytes, gave way to the drier climates of the Permian, where deserts dominated the heart of the supercontinent. Evolution never rested, constantly testing, shaping, and discarding life forms in response to the ever-changing environment. The idea of Pangea holds a certain meditative beauty. Imagine lying down at night, listening to the slow creaks of Earth's crust, hearing the wind sweep across endless plains without borders. In that stillness, you can sense the rhythm of geologic time, immense, patient, almost eternal. For a moment, your own life feels small compared to the continent's wanderings, yet comfortingly part of something much greater. In this first section, we've only touched the surface. What Pangea was, why it formed, and why it matters. In the following sections, we will wander through the lush forests of the Carboniferous, cross the sun-scorched deserts of the Permian, watch mountains rise, oceans shift, and species adapt. Step by step, you will see the Earth as it once was. In all its unity and diversity, this is not just a documentary of science, but also a journey meant to calm the mind, so let your thoughts slow down. With each description, allow yourself to imagine the world as it was, drifting into the stillness of geological time. As we continue our exploration of life on Earth during Pangea, the Earth has never been still. Though mountains seem eternal and oceans feel infinite, both are only temporary expressions of the planet's deeper rhythm. Beneath our feet, the crust floats on a mantle that moves with almost imperceptible slowness. Over millions of years, these movements guide entire continents into long journeys across the globe. Pangea was the result of one such grand migration. To understand how Pangea came to be, imagine the Earth about 400 million years ago in the late Devonian period. At that time, the surface of the planet looked nothing like today. Instead of 7 separate continents, there were smaller land masses scattered across the globe: Laurentia, Baltica, Siberia, Gondwana, and others. Each drifted across the surface like colossal rafts of stone, driven by forces deep within the earth. These continents were slowly but steadily converging. Drawn together by plate tectonics, the invisible engine that constantly reshapes our world. The story begins with Gondwana, a massive landmass that already included what we now know as South America, Africa, Antarctica, India, and Australia. To the north, smaller continents like Laurentia, which would one day become North America, and part of Europe and Baltica drifted closer. The collision of Laurentia and Baltica with smaller microcontinents formed an early version of the supercontinent known as Euromerica, sometimes called Laurussia. This was one of the first steps toward the eventual assembly of Pangea. Over millions of years, these landmasses continued to drift, closing oceans between them. One of the most significant events in this slow-motion dance was the collision between Gondwana and Euromerica. The two continents converged with tremendous force, crumpling the crust and giving birth to enormous mountain ranges. Among them was the Hercynian orogeny in Europe and the Alleghanian orogeny in North America. Geological events that would later leave behind ranges such as the Appalachian Mountains. Even today, when you walk among the worn ridges of the Appalachians, you are treading on the scars of Pangea's birth. As the continents pressed together, oceans disappeared. One such ocean was the Rheic Ocean, which once separated Gondwana from Euromerica. Over time, it narrowed and vanished, consumed by the movement of tectonic plates. Its disappearance symbolized a step closer to the creation of a united supercontinent, but Pangea was not yet complete. To the northeast, the Siberian continent drifted into position, while smaller land masses called microplates were absorbed along the way. The assembly reached its final stages by around 335 million years ago, during the late Carboniferous period. By then, Earth had transformed into a world with one massive landmass surrounded by one immense ocean. The age of Pangea had begun. The unification of the continents did more than reshape geography, it altered climate, its ecosystems, and the evolutionary path of life itself. When continents fuse, their interiors are pushed far from the moderating influence of oceans. This creates vast stretches of landlocked environments, where climates become more extreme. In the case of Pangea, a massive desert stretched across the center of the supercontinent, while coastal regions hosted lush forests and swamps. This diversity of habitats created both opportunities and challenges for life. If you try to picture this assembly, imagine continents moving silently across millions of years, colliding slowly yet with unstoppable force. Imagine towering mountains, rising where plates collided, and long shallow seas disappearing as landmasses squeezed them shut. The earth groaned and shifted, but in its patience, sculpted a new world. It is humbling to think that the continents we know today, North America, South America, Europe, Africa, Asia, Australia, and Antarctica once, sat together, joined in a single landmass. Their later separation would shape human history, determining how civilizations arose, how animals and plants spread, and even how cultures encountered one another. But long before humans appeared, this great union of land had already written its chapter in Earth's story. When you look at a modern map, you can still see echoes of Pangea's assembly. The matching coastlines of South America and Africa are no coincidence. They were once joined. The Appalachian Mountains in North America align with ranges in northern Europe and northwest Africa, remnants of the same collision. These clues, scattered across the planet, are like puzzle pieces that reveal the ancient story of Pang. As we close this section, imagine drifting gently across geological time. Oceans vanish, continents merge, and mountains rise, but all on a scale so slow it feels like eternity. The birth of Pangea was not sudden. It was the culmination of hundreds of millions of years of motion. Yet once formed, it set the stage for dramatic changes in life and climate. Changes we will explore in the next sections. For now, let your mind rest on this image. A single supercontinent. Newly born, cradled by a vast ocean, silent except for the whisper of wind and the distant roar of waves. Earth had entered a new age, the age of Pangea. When Pangea first came together, the Earth was alive with green abundance. The late Carboniferous period, about 335 to 300 million years ago, was an era when dense forests stretched across much of the supercontinent's tropical and subtropical zones. These forests were unlike anything we see today. Towering above the landscape were not oaks or pines, but giant club mosses, horsetails, and ferns. Some of these plants, like lepidodendron and sigillaria, grew to heights of more than 30 meters, forming vast swampy jungles that darkened the ground below. Their trunks were scaly, their leaves long and narrow, and their reproduction depended not on flowers or seeds, but on spores released into the humid air. The Carboniferous swamps were the engines of a great natural experiment. As plants grew, died, and fell into stagnant waters, they did not fully decay. Over millions of years, layers of partially decomposed vegetation compressed into seams of coal. Much of the coal we mine today, the black rock that fueled the Industrial Revolution, comes from these ancient swamp forests of Pangea's early days. In this way, the forests of Pangea still power our modern world. Their energy preserved across deep time. But forests were only part of the story. In the wetlands and rivers, amphibians thrived. Salamander-like creatures, some as large as crocodiles, crept among the roots and swam through shallow waters. This was the age when amphibians reached their greatest diversity, benefiting from the warm, moist climate of the supercontinent's tropical belts. Yet the swamps were also home to newcomers creatures that would soon dominate the Earth, the reptiles. Unlike amphibians, reptiles had tough, scaly skin and eggs with protective shells. This allowed them to venture away from water and colonize the drier interiors of Pangea. Small at first, they represented a quiet revolution in evolution. 1. That would lead eventually to the dinosaurs, and much later. 2. Birds and mammals. Above these early forests, giant insects filled the skies. Dragonflies with wingspans of nearly 70 centimeters darted through the humid air. Millipedes longer than a human arm crawled among the undergrowth. These oversized creatures thrived because of higher oxygen levels in the atmosphere, which allowed their bodies to grow far larger than their modern descendants. For a time, Earth belonged to forests and the invertebrates that filled them. As Pangea's continents pressed tighter together, climates began to shift. The interior of the supercontinent became drier, cut off from the moderating influence of the ocean. Deserts began to spread, especially during the Permian period, around 299 to 252 million years ago. The lush swamps retreated, giving way to hardy conifers and seed ferns adapted to arid conditions. The transition was slow but profound. The world of sprawling wetlands gave way to a harsher, more seasonal environment. Life adapted. Amphibians declined as reptiles diversified. Some reptiles evolved into large herbivores and carnivores, dominating the land in a variety of forms. One of the most remarkable groups of the Permian was the synapsids, often nicknamed mammal-like reptiles. Among them was Dimetrodon, a predator recognizable by the great sail on its back, supported by elongated spines. Though it looked like a dinosaur, it was not one that lived long before dinosaurs arose. Synapsids represent the ancestors of modern mammals, carrying within them the first hints of traits that would one day give rise to warm-blooded creatures like us. The forests and deserts of Pangea also influence the atmosphere, with fewer swamps producing coal and fewer dense forests capturing carbon dioxide. Earth's climate entered cycles of fluctuation. At times, glaciations cooled parts of the southern supercontinent, while the central deserts remained scorching hot. This contrast created ecosystems of striking diversity, from icy highlands to parched deserts, from coastal mangroves to inland forests. As we imagine walking through Pangea's landscapes, picture yourself moving from the shadowy undergrowth of a carboniferous swamp, buzzing with giant dragonflies, into the dry, open plains of the Permian interior, where reptilian footprints press into the red sand. Picture vast herds of plant-eating reptiles grazing among seed ferns, while predators stalk the horizon. Overhead, the skies are immense and endless, the air heavy with dust and heat. It was a world both alien and familiar, shaped by the joining of continents into one. The ecosystems of Pangea remind us of the resilience of life. Whether in swamps rich with oxygen or deserts baked under a relentless sun, life found a way to thrive, to adapt, to prepare for what was yet to come. In the next section, we will explore the climates of Pangea in greater detail, the vast deserts, the monsoons, the polar ice, and how these extremes shape the destiny of life on this ancient earth. For now, let your mind linger in the quiet of those primeval forests. Imagine the rustle of fern fronds in the humid breeze, the distant splash of an amphibian slipping into dark water, the faint drone of giant insects. The earth was alive, vibrant, and restless, beginning a story that would last millions of years. When Pangea stretched across the earth, the very shape of the supercontinent reshaped the climate. On today's fragmented globe, oceans and coastlines help to distribute moisture and moderate temperature, but Pangea was different. With almost all land bound together in a single mass, enormous regions lay far from the sea, cut off from its cooling breezes and nourishing rains. The result was a world of extremes, blistering deserts in the heart of the continent, fertile coasts along its edges, icy poles, and powerful seasonal winds that swept across its vast expanse. At the center of Pangea lay what may have been the largest desert the Earth has ever known. Imagine endless red sand stretching across the horizon, broken only by rocky plateaus and sparse vegetation. The heat would have been intense during the day, with little relief at night. Without nearby oceans to provide moisture, rain rarely reached the interior. Fossilized dunes, now preserved in ancient sandstone formations across regions like the southwestern United States, northern Africa, and parts of Europe, are the silent testimony of this vast, arid heartland. In those sands, footprints of reptiles and early synapsids are sometimes found, showing that even in this harsh land, life found ways to survive. In contrast, along the coasts of Pangea, conditions were very different. Here seas moderated the climate, bringing rainfall and humidity. Swamps, mangroves, and forests flourished along these coastal regions, sustaining a great variety of life. Rivers carried nutrients from the mountains into deltas, where ecosystems thrived. For creatures adapted to moisture, amphibians, insects, and lush plant life, these margins of the supercontinent were havens of abundance. The sheer size of Pangea also shaped its weather patterns in extraordinary ways. One of the most striking features was the development of monsoon systems. As seasons changed, vast areas of land heated and cooled, creating massive differences in air pressure. In summer, hot air rising from the supercontinent pulled in moist winds from Panthalassa, unleashing torrential rains along the coasts and near marginal seas. In winter, the process reversed, and cold, dry winds swept outward across the land. These seasonal monsoons could have been far more powerful than those we know today, simply because of Pangea's immense size. Imagine rains so heavy they carved valleys. Followed by months of unrelenting dryness, this was the rhythm of life along the supercontinent's edges. At higher latitudes, the climate revealed another extreme. In the southern portion of Pangea, what is now Antarctica, South America, southern Africa, and Australia, glaciers advanced and retreated through time. Evidence of glaciation scratched rocks, deposited boulders, and layers of glacial till shows that even during a time when much of the Earth was hot, the southern supercontinent endured icy conditions. This was a reminder that Earth's climate system is complex. It's influenced not only by geography, but also by atmospheric composition, orbital cycles, and volcanic activity. Meanwhile, the north of Pangea often baked under intense heat, deserts dominating. Regions that today are Europe, Asia, and North America. The combination of scorching summers, cold winters, and low rainfall created environments similar to modern deserts, but on a scale we cannot fully imagine. Sand seas stretched for hundreds of kilometers, Winds sculpted dunes into vast patterns that can still be traced in ancient rock formations. These deserts were not empty, though they were home to hardy reptiles, burrowing animals, and drought-tolerant plants. Life adapted to survive in niches where water was rare and the sun unrelenting. Volcanism also played a role in shaping Pangea's climate, though in its existence, the shifting of tectonic plates created mountain ranges and rift valleys. While volcanic eruptions released gases into the atmosphere, some of these gases, like carbon dioxide, warmed the planet, while others, like sulfur aerosols, could temporarily cool it. The balance of these forces meant that Pangea's climate was not stable, but ever-changing. Periods of warmth were followed by intervals of glaciation, creating cycles of adaptation and extinction for the organisms that lived there. The vast size of Pangea had another consequence: continentality. Modern climates are often moderated by the sea. In Europe, for instance, the Atlantic Ocean softens winters and summers alike. But deep within Pangea, thousands of kilometers from the nearest coast, no such moderation existed. Summers grew hotter, winters colder, and rainfall scarcer. The result was a climate more extreme than anything experienced by humans today. These extremes profoundly influenced evolution. Amphibians, dependent on water, declined as drier conditions spread. Reptiles, with their scaly skin and amniotic eggs, thrived. Plants evolved to withstand aridity, developing seeds that could survive dry conditions. And in the oceans surrounding Pangea, life experienced its own cycles of abundance and hardship, driven by changing sea levels and shifting temperatures. For us, imagining such a climate can feel overwhelming, yet also strangely calming. Close your eyes and see it. Storms gathering along the edges of the continent, lightning flashing above monsoon rains, while far inland, desert winds whip across empty dunes. To the south, glaciers grind across valleys, carrying boulders the size of houses. Across the globe, life endures, adapting to each extreme, never ceasing to find a foothold. Pangea's climate teaches us about resilience. It shows that Earth has always been a place of change, where environments transform and life must either adapt or vanish. It also whispers a reminder: the climates we know today are temporary. In deep time, nothing is fixed. Oceans close, deserts bloom, glaciers melt, and forests rise again. As we move into the next section, we will leave behind the winds and deserts and look instead at the mountains and seas of Pangea, the colossal ranges born of collisions, and the shallow inland waters that nourished unique ecosystems. For now, rest your thoughts on this vision: a world of vast contrasts, a supercontinent of extremes, where deserts, monsoons, and ice coexisted, and where life, in all its tenacity, continued its timeless dance with the planet. The collision of continents that forged Pangea did more than simply unite the land. It reshaped the surface of Earth in dramatic ways. Where plates met, the crust buckled and rose, pushing mountains skyward. Where basins sank, seas flooded in, forming inland waters teeming with life. These landscapes, towering ranges, and shallow seas gave Pangea a diversity that balanced its deserts and forests, shaping the habitats of countless species. One of the most iconic results of Pangea's assembly was the birth of mountain chains. When Gondwana and Euro-America collided, the impact was titanic, folding and uplifting the crust into ranges that dwarfed much of what we see today. In what is now eastern North America, the Alleghanian orogeny raised the Appalachians to Himalayan heights. Imagine jagged peaks, freshly carved by uplift, capped with snow, their flanks clothed in conifer forests. Today, the Appalachians appear as gentle ridges, softened by hundreds of millions of years of erosion. But in the time of Pangea, they stood sharp and young, monuments to the planet's restless power. Across the Atlantic, Europe bore its own scars of Pangea's birth. The Variscan, or Hercynian orogeny, produced mountain ranges that once stretched across France, Spain, Germany, and beyond. These too have worn down with time, their remnants now rolling hills and ancient outcrops. Yet, in the days of Pangea, they would have formed an unbroken chain, spine of stone running across the northern hemisphere. Further east, the story continued. As Siberia, Kazakhstan, and other smaller landmasses joined the supercontinent, mountain belts rose in Central Asia. Over millions of years, these collisions created the foundations of ranges that would later be reshaped into parts of the Urals. And other mountain systems? The merging of land was never silent. It was a symphony of earthquakes, eruptions, and uplift. A slow crescendo of stone echoing through geologic time. Mountains influenced more than scenery. They shaped climate, diverting winds, casting rain shadows, and creating rivers that carried nutrients into lowlands. Valleys carved between peaks provided sheltered habitats where unique ecosystems flourished. Rivers rushing down slopes fed swamps and deltas, sustaining amphibians, reptiles, and the forests of ancient seed ferns. Mountains, in their grandeur, also served as natural corridors and barriers, guiding the spread of species across the supercontinent. But Pangea was not only mountains and deserts. It also contained shallow inland seas, where water pooled in basins within the supercontinent. These seas were not vast like Panthalassa, but were shallow, warm, and rich in nutrients. One of the most famous examples is the Zechstein Sea, which existed in what is now Central and Northern Europe during the late Permian. Its warm waters evaporated repeatedly, leaving behind thick deposits of salt, gypsum, and other minerals that we still mine today. Inland seas like the Zechstein were oases in the arid interiors of Pangea. They supported marine life fish, mollusks, corals, and created wetlands along their margins where terrestrial and aquatic worlds mingled. Fossils from these basins reveal ecosystems where reptiles hunted along shores and amphibians clung to the last remnants of watery refuges. For many species, these inland waters were lifelines in an otherwise harsh environment. The interplay of mountains and seas also influenced evolution. As mountain ranges formed barriers, populations of plants and animals became isolated, adapting to their specific environments. In inland seas, unique species evolved, adapted to brackish or evaporative waters. These localized ecosystems enriched biodiversity. Even as the broader climate of Pangea became more challenging, picture yourself standing on Pangea during this time. To one side, a line of mountains rises against the sky, their peaks glowing. In the light of a Permian sunset, snowmelt tumbles down their slopes, carving rivers that wind into the distance. To the other side, a shallow inland sea glimmers, its surface dotted with islands and bordered by wetlands buzzing with life. The air smells of resin from conifers and salt from evaporating pools. This world, though ancient, feels alive and dynamic. Shaped by forces still at work today, even far inland, the presence of seas created microclimates. Breezes from these bodies of water softened the harshness of nearby deserts, while salt flats and mineral deposits created stark alien landscapes. When seas dried, they left behind basins of layered rock, archives of Earth's shifting climate. These deposits studied today tell us not only about geology, but also about the chemistry of ancient oceans. The gases in the atmosphere and the cycles of evaporation and renewal that pulsed across Pangea, the supercontinent was not static. Over millions of years, its mountains eroded, its seas dried, and new ones appeared. Rivers shifted course, carving canyons and building deltas. Life responded with resilience, forests retreating from arid lands, reptiles spreading into deserts, and amphibians clinging to every patch of water they could find. Mountains and seas gave Pangea its contrasts. Where mountains towered, ecosystems clustered in cool, wet valleys. Where seas spread, life flourished in shallow waters. And between them stretched deserts, plains, and forests, each offering its own trials and opportunities. It was this complexity that made Pangea both harsh and hospitable, a place where life was tested, but also where it could innovate and evolve. As we leave this section, let the image linger. Towering mountain chains, sharp and new, casting shadows over quiet inland seas. In those shadows, life thrived, adapted, and prepared for the next great challenges of Earth's history. In the next section, we will dive beneath the waves of Panthalassa. It's a great ocean that encircled Pangea, and explored the marine worlds that mirrored the drama on land. Surrounding Pangea, like a vast, eternal embrace, was a single world-spanning ocean, Panthalassa. Its name, from the Greek words pan meaning all, and thalassa meaning sea, translates to the universal ocean. While today, our globe is divided into distinct seas, the Atlantic, Pacific, Indian, Arctic. In southern, during the reign of Pangea, there was only one immense, unbroken expanse of salt water. Panthalassa covered nearly 70% of Earth's surface, stretching from pole to pole, horizon to horizon. A blue infinity with no land in sight once you left the supercontinent's coasts. To imagine Panthalassa is to imagine vastness itself. Picture standing on a shoreline of Pangea. Behind you, endless desert or forest. Before you, a horizon that seems never to end. Waves roll ceaselessly, driven by winds that sweep across thousands of kilometers of open water. Sunlight sparkles. Across its surface, yet beneath, lies a world as rich and complex as any on land. The currents of Panthalassa were powerful and intricate, shaped by the enormous size of the ocean and the configuration of Pangea. Because there was only one global ocean, circulation patterns may have been both simpler and more extreme than today. Warm equatorial waters spread outward, while polar regions grew icy cold. These currents not only influenced marine ecosystems, but also affected climate on the supercontinent itself, carrying moisture to coasts and helping drive the powerful monsoons that lashed its margins. Beneath the waves, life flourished in extraordinary diversity. Coral reefs, though made of different species than the reefs we know today, stretched along shallow continental shelves. These reefs were havens for fish, mollusks, sponges, and a host of marine invertebrates. Trilobites, though in decline, still scuttled across the seafloor in some regions. Brachiopods, crinoids, and ammonites dominated the seas, they're fossilized. Shells today scattered across rocks on every continent. Among the most striking inhabitants of Panthalassa were the ammonoid spiral-shelled relatives of the modern squid. They drifted and swam through the waters, some small as a coin, others larger than a human head. Their coiled shells, now common fossils, were once homes to living creatures that hunted smaller fish and plankton in the open ocean. Alongside them swam early sharks, streamlined and efficient. Patrolling the waters as apex predators, Panthalassa also hosted unique ecosystems along its coasts. In shallow lagoons and inland seas that connected with the great ocean, strange communities of organisms thrived. Algae carpeted warm shallows, feeding schools of fish and the invertebrates that preyed on them. Reptiles, newly adapted to life near the water, occasionally ventured along the shorelines, blurring the line between land and sea. The deep ocean, far from shore, was a place of mystery. Sunlight could not penetrate its depths, yet life still endured. Tiny plankton drifted in endless numbers, forming the base of the food chain. As they lived and died, their remains drifted down like marine snow, nourishing creatures of the abyss. Some of these deep dwellers, preserved only in rare fossils, remind us that Panthalassa's depths were as vibrant and mysterious as its surface. But Panthalassa was not always peaceful. Its size allowed for storms of unimaginable power. With no other continents to break the winds, cyclones may have raged with an intensity we cannot easily fathom. Gigantic waves, driven by unbroken winds, would have thundered against Pangea's coastlines. These storms reshaped beaches, carved cliffs, and influenced the survival of life along the shores. The ocean also played a central role in the cycles of life and death on Earth, as tectonic activity reshaped the ocean floor. Volcanic ridges rose beneath the waves, releasing heat and minerals into the water. These undersea volcanoes created oases where strange organisms gathered, feeding not on sunlight but on the chemicals pouring from hydrothermal vents. Panthalassa, in this way, was both a stable cradle of life and a restless arena of geological change. For the creatures of Pangea, the ocean was both barrier and opportunity. It separated populations, isolating them into distinct evolutionary paths. Yet it also provided corridors of connection, as currents carried larvae and plankton across thousands of kilometers. Over millions of years, Pangea helped shape the course of evolution by deciding who stayed apart and who mingled in its waters. As we reflect on Pangea, we should remember that much of its story is written in stone. Fossils of ammonites, brachiopods, crinoids are scattered across modern mountains and deserts places, once under its waters. Limestone cliffs that now rise in Europe, North America, and Asia began as seafloor sediments in Pangea. Every shell, every ripple of rock, is a quiet memory of the ocean that once ruled Earth. Close your eyes and let the image form: an endless ocean. Waves rising and falling with the pull of the moon, stars mirrored on its dark surface at night. Beneath, schools of fish shimmer like liquid silver. Ammonites drift in spiral grace, and ancient sharks prowl in silence. The ocean breathes in its eternal rhythm, vast and serene, surrounding the land that would one day shape our own existence. Pangea was not merely the backdrop to Pangea's story, it was half of it. Without the ocean, the supercontinent would not have had its monsoons, its climates, or its cycles of life. Land and sea were partners in this ancient world, and together they shaped the path of life. In the next section, we will turn from the waters back to the land, exploring the rise of early reptiles and the ancestors of mammals, creatures that began to dominate Pangea's dry interiors and left behind a legacy that leads directly to us. As Pangea settled into its mighty form, life upon the land began to change in profound ways. The warm swamps and forests of the Carboniferous had favored amphibians, creatures bound to water for breeding and survival. But the climate of Pangea was shifting. Deserts spread across its interiors, seasonal extremes tested resilience, and rivers sometimes ran dry. It was in this changing world that reptiles, with their remarkable adaptations, began to rise. The key to their success lay in something deceptively simple: the amniotic egg. Like amphibians, which laid soft eggs that required moist environments, reptiles evolved eggs encased in protective shells. These shells shielded embryos from desiccation, allowing them to be laid on land far from ponds or swamps. Inside the egg, membranes provided nourishment and waste management, a self-contained life support system. This evolutionary innovation freed reptiles from the chains of water, opening the vast dry interiors of Pangea to colonization. Soon reptiles diversified into many forms. Small lizard-like species scurried among rocks and shrubs, feeding on insects. Larger herbivores roamed plains, using sturdy jaws to chew on tough vegetation. Carnivorous reptiles stalked them, their bodies lean and agile, their teeth sharp for slicing flesh. Some evolved armored plates for protection, while others developed sails or crests, perhaps for display, thermoregulation, or intimidation. Among these creatures were the synapsids, sometimes misleadingly called mammal-like reptiles. They were not true reptiles, nor yet mammals, but something in between, a branch of life experimenting with traits that would eventually define us. Synapsids had skulls, with a single temporal opening behind each eye, a feature that distinguished them from reptiles. This opening allowed stronger jaw muscles, giving them a more powerful bite. Over time, their bones and physiology shifted toward features we recognize in mammals: differentiated teeth, more upright postures, and in some cases, hints of warm-bielodoness. One of the most famous synapsids of Pangea was Dimetrodon, a predator often mistaken for a dinosaur. With its massive sail rising from its back, supported by elongated vertebral spines, it was a striking sight on the Permian plains. The sail may have helped regulate body temperature, absorbing heat in the morning and releasing it later, or it may have been used for display, signaling dominance or attracting mates. Dimetrodon was a top predator of its time, feeding on amphibians, smaller reptiles, and even early synapsids. But not all synapsids were hunters. Some, like Edaphosaurus, were herbivores, also equipped with sails, but feeding on plants instead of flesh. Their teeth were adapted for grinding vegetation, and their bulky bodies suggested a life of grazing across the sparse vegetation of Pangea's semi-arid regions. The coexistence of carnivorous and herbivorous synapsids reflected the growing complexity of ecosystems during the Permian. Reptiles, too, were diversifying. Groups like the parareptiles, camptorhinids, and proterosaurs explored niches from insect hunting to herbivory. Their sturdy bodies and scaly skins protected them against dehydration, making them well-suited to Pangea's deserts and savannas. Some reptiles even began returning toward the water's edge, experimenting with amphibious lifestyles that would one day give rise to marine reptiles of later eras. The rise of reptiles and synapsids reshaped the food web of Pangea. Amphibians, once dominant, now retreated into shrinking wetlands, their numbers dwindling. Insects remained abundant, fueling the diets of smaller reptiles. Plants adapting to drier climates evolved seeds and tougher leaves, providing resources for grazing, synapsids, and reptiles alike. Carnivores grew larger and more specialized, honing the arms race of survival. What made synapsids so special was not only their adaptations, but also their potential. In their bones, we see the foreshadowing of mammals, their teeth differentiated into incisors, canines, and molars, a pattern mirrored in our own mouths. Their jaws and skulls shifted toward more efficient chewing, allowing varied diets. Some may have developed whisker-like sensory hairs, a hint of the fur that would later characterize mammals. And deep within their lineage lay the origins of warm-bloodedness, a trait that would allow mammals to thrive in climates both hot and cold. Standing on Pangea, imagine the scene: a broad savanna under a blazing sun, where Dimetrodon basks, its sail catching the light. Nearby, a herd of Edaphosaurus grazes among low plants, their sails rising like banners in the heat haze. Small reptiles scuttle under rocks, avoiding predators overhead. In the distance, amphibians linger in shrinking pools, reminders of an earlier age now fading. This was a transitional world, where the baton of dominance was being passed from one group of creatures to another. The story of reptiles and synapsids on Pangea is not only about survival, but also about experimentation. Evolution was testing new designs, some of which would endure, others that would vanish in extinction. The diversity of forms reveals nature's creativity, its endless capacity to adapt and reimagine life for changing conditions. As night falls in your imagination, picture these creatures resting. The stars shine over Pangea's deserts, and the distant roar of waves from Panthalassa reaches the land. Da-da-da-da. In the stillness, reptilian eyes gleam in the dark, ever watchful, ever resilient. Life was preparing for its next great chapter. In the next section, we will explore that chapter further: the plants and ecosystems of Pangea forests, seed ferns and conifers that painted the land green and sustained the creatures of this ancient supercontinent. If the animals of Pangea roamed, hunted, and grazed across its plains, then it was the plants that laid the foundation for all life. Silent yet powerful, they painted the supercontinent in shades of green, shaping not only ecosystems but also the very atmosphere that life breathed. From humid swamps to arid deserts, the plant kingdom of Pangea revealed extraordinary variety, adapting to every niche the ancient climate offered. At the dawn of Pangea's existence, during the late Carboniferous, lush forests dominated much of the tropical belts. Towering lycophytes plants like Lepidodendron and Sigillarios like living pillars, their trunks straight and scaled, their crowns a fan of narrow leaves. Horsetails such as calamites stretched high, while ferns spread wide carpets of green across the forest floor. These swampy jungles were humid and dense, filled with the hiss of insects and the croaks of amphibians. Their fallen trunks and leaves sank into waterlogged soils, slowly compressing into the seams of coal that would one day fuel human civilization. But as Pangea's climate shifted, so too did its flora. The spreading deserts and seasonal climates of the Permian brought challenges that many swamp plants could not survive. In their place rose new champions, seed plants. Unlike spore-bearing plants that needed constant moisture, seed plants enclosed their offspring in protective coats, allowing them to survive drought and cold. This innovation paralleled the reptile's amniotic egg. Both strategies freed life from dependence on water, opening new frontiers across the SUP or second. Among these seed plants were the pteridosperms, or seed ferns. Despite their fern-like appearance, they reproduced with seeds, not spores. They filled landscapes once dominated by lycophytes, spreading into semi-arid regions where older plants could not endure. Alongside them grew conifers, ancestors of today's pines and firs. With needle-like leaves adapted to conserve water, their resin-scented forests stretched across uplands and dry interiors, providing shelter and food for reptiles and snids. In wetlands and coastal margins, other plant groups flourished. Glossopterids, an important group of seed ferns, spread across the southern regions of Pangea, what is now Antarctica, South America, Africa, and Australia. Their distinctive tongue-shaped leaves carpeted landscapes, forming vast forests that sustained herbivores. The fossil remains of Glossopteris leaves are today one of the strongest pieces of evidence for continental drift, found scattered across continents that were once joined in Gondwana. Forests of Pangea played a vital role in shaping the planet's atmosphere. During the Carboniferous, the abundance of swamp plants absorbed immense amounts of carbon dioxide, releasing oxygen in return. Oxygen levels soared, reaching up to 30 to 35%, far higher than today's 21%. This enriched atmosphere not only allowed giant insects to thrive, but also influenced fire frequency and the metabolism of animals. Later, as swamps declined and deserts spread, oxygen levels fell, reminding us how closely life and atmosphere intertwine. Plants also structured the ecosystems of Pangea. Herbivores depended on them for food, from small insect-eating reptiles nibbling seeds to massive synapsids grazing leaves. Carnivores, in turn, depended on the herbivores, creating food chains rooted firmly in green life. Fallen logs provided shelter, forests offered shade, and seasonal cycles of growth and decay set the rhythm for all creatures. Even deserts, seemingly barren, were dotted with hardy shrubs and early conifers. Supporting life adapted to scarcity. Walking through a Pangean forest in your imagination, you would find a landscape both alien and familiar. Towering seed ferns stretched overhead, their fronds filtering the sunlight into a soft green glow. Conifers stood in silent rows, their resin scent heavy in the air. Insects buzzed among the leaves, dragonflies darted near streams, and small reptiles rustled through undergrowth. Occasionally, a massive trunk would lie toppled on the ground, its bark already home to fungi and insects, recycling its matter back into the soil. The plants of Pangea also tell us about connection. Fossil leaves, seeds, and pollen found across continents provide evidence that these lands were once joined. A Glossopteris leaf found in Antarctica matches one from India. A conifer fossil in South America resembles one in Africa. These green records, preserved in stone, are silent but powerful witnesses of the time when Earth's continents were one. As Pangea endured through millions of years, its vegetation changed with the climate. In wetter intervals, forests expanded. In drier times, deserts pushed them back. But always, plants adapted. They were the patient architects of life, building soils, capturing sunlight, cycling nutrients, and preparing the ground for future ecosystems. Without them, the reptiles, synapsids, insects of Pangea could never have thrived. Close your eyes and picture it now. The whisper of wind in conifer needles, soft sway of seed fern fronds, the golden glow of a Permian sun filtering through leaves. This was the green kingdom of Pangea, silent, steadfast, and essential. In the next section, we will shift our gaze to the insects and early flying creatures of Pangea, the buzzing giants of the Carboniferous skies and the delicate-winged pioneers that filled the air above the supercontinent. Long before birds spread their wings, before pterosaurs glided across the skies, it was the insects that ruled the air. During the age of Pangea, the sky above the forests, swamps, and deserts was alive with the whir of wings, the shimmer of carapaces, and the hum of creatures that had mastered flight millions of years before vertebrates ever tried. The Carboniferous period, just before and during the early formation of Pangea, was the golden age of giant insects. Oxygen levels in the atmosphere were unusually high, up to 35% compared to today's 21%. This abundance of oxygen allowed arthropods to grow to sizes unimaginable in our modern world. Since their breathing systems depended on passive diffusion, in the rich air of Pangea, this limitation was lifted and insects expanded into giants. One of the most iconic of these was Meganeura, a dragonfly-like predator with a wingspan of nearly 70 centimeters. Imagine walking through a swampy forest and hearing the thunderous beat of wings overhead as a creature the size of a raven swooped past. Meganeura hunted smaller insects and perhaps even small amphibians, patrolling the skies with unmatched dominance. Its compound eyes scanned every movement, while its long legs snatched prey mid-flight. On the forest floor, other arthropods reached massive proportions. Arthropleura, a millipede-like creature, stretched over 2 meters in length, sliding silently through leaf litter. Though primarily a detritivore, feeding on decaying plants, its sheer size would have made it a startling sight. Giant cockroaches, crickets, and beetle ancestors filled the undergrowth, feeding the food web that sustained reptiles and amphibians. As time passed and oxygen levels decreased, many of these giants faded, yet insects remained masters of diversity. By the Permian period, they had evolved into a wide array of forms: early beetles with hardened wing cases, true bugs with piercing, sucking mouths, and primitive relatives of grasshoppers and mantises. Each had carved out niches in the forests, plains, and deserts of Pangea, adapting to feed on plants, prey, or decaying matter. Flight itself was one of the greatest evolutionary achievements in Earth's history. With wings, insects could escape. Predators travel between habitats and exploit food sources far apart. They became pollinators, though flowering plants would not appear until much later in the Mesozoic. Even without flowers, insects played crucial roles in ecosystems, breaking down plant material, cycling nutrients, and supporting food webs as both predator and prey. The skies of Pangea were never empty. Picture, if you will, a warm Carboniferous evening, the air thick with humidity, the scent of ferns and wet soil heavy around you. Suddenly, a massive Meganeura darts overhead, its wings catching the last golden rays of the sun. Nearby, swarms of smaller insects rise in a shimmering cloud, their bodies flashing iridescent green and copper. The air vibrates with their collective hum. Below, amphibians snap at them with sudden lunges, while reptiles lie in wait, learning to exploit this. Airborne feast. By the late Permian, the diversity of insects had exploded. Fossil evidence shows more than a dozen distinct insect orders thriving across Pangea, many of which still have descendants today. Early beetles gnawed at wood, recycling dead trunks. True bugs pierced seeds and leaves. Dragonflies, though reduced in size, remained swift aerial hunters. Each innovation in mouthparts, wings, or body design allowed insects to colonize new niches, ensuring their survival through extinction events that would wipe out other groups. Insects were also silent recorders of climate. Their fossils show how vegetation shifted, how deserts expanded, how wetlands retreated. Their wings and bodies preserved in stone tell us which regions were lush with life and which were harsh and dry. Some even preserved delicate patterns, veins in wings as fine as lace, whispering to us across hundreds of millions of years. Though insects were the first to fly, they were not alone in the skies forever. As Pangea's story unfolded, other creatures began experimenting with gliding and flight. Some reptiles evolved skin flaps to glide between trees, a faint preview of the soaring pterosaurs to come in the Triassic. But during the height of Pangea, insects were unrivaled in the air, their dominance shaping entire ecosystems below. Their importance cannot be overstated. They pollinated early seed plants, dispersed spores, broke down organic matter, and served as food for amphibians, reptiles, and synapsids. Without insects, the web of life on Pangea would have unraveled. As you let your thoughts drift now, picture lying beneath the canopy of a Pangean forest, listening not to birdsong, but to the ceaseless chorus of buzzing wings. Imagine enormous dragonflies casting shadows across the swamp, beetles scurrying among bark, and crickets singing under the stars. The world was alive with motion. The air itself, a stage for life's experiments. In the next section, we'll turn to a darker chapter of Pangea's story, the mass extinctions that tested life's resilience, reshaping ecosystems and paving the way for new eras. For now, let the image of a sky alive with wings linger in your mind, a reminder of how long ago life learned to conquer the air. Life on Pangea was resilient, diverse, and inventive. Plants colonized deserts, reptiles roamed plains, insects filled the air, and synapsids pushed evolution toward the path that would one day lead to mammals. Yet hidden beneath this vitality was a truth as old as Earth itself. Extinction is part of the story. For every rise, there comes a fall. And during the age of Pangea, the planet endured some of the greatest crises it has ever known. The most infamous of these was the Permian-Triassic extinction event, often called the Great Dying. It occurred about 252 million years ago, near the end of the Permian period, and it remains the largest mass extinction in Earth's history. Scientists estimate that around 90 to 95% of marine species and 70% of terrestrial vertebrate species vanished, whole forests withered, oceans emptied, and ecosystems collapsed. Life itself seemed on the brink of annihilation. What could cause such devastation? The evidence points to a combination of catastrophic forces. In what is now Siberia, one of the greatest volcanic outpourings in history erupted, the Siberian Traps. For nearly 1 million years, immense lava flows covered vast areas of land, releasing enormous amounts of gases into the atmosphere. Dioxide and methane warmed the planet dramatically, while sulfur dioxide triggered acid rain. Oceans acidified, corals and shell-building creatures dissolved, and rising temperatures created stagnant, oxygen-poor waters. Methane hydrates trapped in seafloors may have been destabilized, further amplifying global warming. On land, the consequences were equally grim. Deserts expanded as rainfall patterns shifted. Forests died back, taking oxygen production with them. Wildfires may have swept across landscapes, fueled by dry vegetation and high oxygen levels. Herbivores lost their food sources. Predators lost their prey. Even insects, usually the most adaptable of creatures, suffered a severe collapse in diversity. Picture it: rivers drying, skies darkened by volcanic ash, animals fleeing across barren plains. In the oceans, once vibrant reefs bleached and crumbled. Fish gasped in oxygen-poor waters. The great ammonites, trilobites, and brachiopods dwindled. Entire lineages that had endured for hundreds of millions of years ended in this singular catastrophe. Yet, as always, extinction was both an end and a beginning. Out of the wreckage, survivors emerged. A few synapsids clung to existence, small and adaptable. Some reptile groups endured, poised to radiate into new forms. Insects, though reduced, eventually rebounded. Plants returned in hardier forms, with conifers and seed ferns recolonizing devastated lands. The Triassic period that followed would see ecosystems rebuilt, and in that rebuilding, entirely new lineages would appear, including the earliest, dinosaurs. The Permian-Triassic extinction was not the only crisis of Pangea's time. Earlier, during the late Carboniferous and early Permian, smaller extinction pulses had struck, tied to climate shifts and glaciations. These pruned ecosystems, testing resilience again and again. Later, in the Triassic, another extinction event, occurred around 201 million years ago, the Triassic-Jurassic extinction. Though less catastrophic than the Great Dying, it cleared the stage of many large reptiles and amphibians, opening the path for dinosaurs to dominate the Mesozoic world, mass. Extinctions remind us of the fragility of life. For millions of years, Pangea's ecosystems thrived, only to be undone in what must have seemed, in geological terms, an instant. Entire landscapes transformed, and creatures that had ruled vanished forever. Yet they also remind us of resilience. Life endured, evolved, and reimagined itself, even in the wake of unimaginable loss. As you imagine this chapter of Pangea's story, close your eyes and see it slowly. A forest under a darkened sky, its trees silent, its animals gone. Then, after long stillness, green shoots pushing up through ash. Now tiny reptiles scurrying through cracks, insects returning to the air. Life fragile yet unyielding, beginning again. The story of extinction is not only about death, it is about renewal. Pangea bore witness to both, teaching us that even in Earth's darkest hours, life finds a way forward. In the next section, we will turn from these moments of collapse to the creatures that rose from the ashes, the early dinosaurs, the new reptiles, and the species that inherited a wounded but living world. When the smoke of the Permian-Triassic extinction finally cleared, Earth was a wounded planet. Forests were thinned, reefs collapsed, and most animal lineages were gone. But out of this emptiness came opportunity. With ecosystems stripped bare, niches once occupied by synapsid giants and reptilian rulers lay vacant. Into this silence, new forms of life began to rise. Among them were the earliest dinosaurs, creatures that would one day dominate Pangea and define an entire era of Earth's history. At first, dinosaurs were far from dominant. The Triassic world was filled with competition. Surviving synapsids, such as the small adaptable Lystrosaurus, roamed the landscapes of southern Pangea, grazing on tough plants with their beak-like jaws. Archosaurs, the broader reptilian group that included crocodile ancestors and dinosaurs alike, diversified across plains and riversides. Some resembled modern crocodiles, armored and semi-aquatic. Others were nimble hunters racing across dry savannas. Within this diverse cast, the earliest dinosaurs were small, bipedal, and lightly built. Fossils from Argentina, Brazil, and other parts of Pangea reveal creatures like Eoraptor, a swift omnivore no larger than a dog, darting through undergrowth in search of insects, small vertebrates, or plants. Another early dinosaur, Herrerasaurus, grew larger, up to 6 meters long, and hunted as an agile predator, snapping at reptiles and synapsids that crossed its path. These were not yet the giants of the Jurassic, but pioneers testing evolutionary strategies that would eventually bring global dominance. The key advantage of dinosaurs lay in their posture and efficiency. Unlike sprawling reptiles whose limbs extended sideways from their bodies, dinosaurs stood upright, with legs positioned beneath them. This allowed them to move more efficiently, supporting greater endurance and speed. Combined with lightweight skeletons, hollow bones in some lineages, and possibly higher metabolisms, dinosaurs were well suited for the hot, seasonal climates of Triassic Pangea. Over millions of years, dinosaurs radiated into different branches. Some evolved into early sauropodomorphs, long-necked plant eaters that grazed across plains and herds. Though smaller than their later Jurassic descendants, they laid the foundation for giants like Brachiosaurus and Diplodocus. Others became early theropods, agile carnivores with sharp teeth and claws, forebears of both mighty predators like Tyrannosaurus rex and, astonishingly, the birds that fill our skies today. Still others evolved into ornithischians, the herbivores with specialized hips, destined to diversify into armored stegosaurs, horned ceratopsians, and duck-billed hadrosaurs in later epochs. During the Triassic, however, dinosaurs were only one part of a crowded cast. Large reptiles called Rhesuchians, distant relatives of crocodiles, were apex predators in many regions. towering over early dinosaurs. Amphibians like metaposaurs, massive crocodile-like creatures, lurked in rivers and lakes. It is the Triassic war on, climatic shifts, and another extinction event at its end cleared away many of these competitors, leaving dinosaurs to flourish. The landscapes they inhabited were stark and varied. Across the heart of Pangea stretched deserts and seasonal savannas, where small herds of sauropodomorphs browsed low vegetation, watched carefully by lurking predators. Along river deltas, lush vegetation sustained mixed communities of reptiles, amphibians, and insects, while early theropods darted along the shores. In the highlands, conifer forests spread, echoing with the calls of insects and the footsteps of reptiles. Imagine standing on Triassic Pangea at dawn. A dry wind rustles conifer needles, carrying the scent of resin. From behind a grove, a small Eoraptor emerges, alert and cautious, its head tilting as it scans for movement. In the distance, a Herrerasaurus stalks across open ground, its silhouette sharp against the rising sun. The earth beneath your feet still holds the scars of extinction, yet already new life pulses, testing its strength. Dinosaurs at this stage were not the giants that dominate our imagination today. They were opportunists, survivors, and innovators. They succeeded because they were adaptable, efficient, and quick to seize opportunities left by fallen lineages. Over time, these small beginnings would expand into the golden age of dinosaurs, when herds thundered across plains and predators shook the earth with their roars. But here in Triassic Pangea, the story was only beginning. Their rise was also intertwined with Pangea itself. The vast connected landmass allowed dinosaurs to spread quickly across continents. A species that evolved in what is now South America could migrate across Africa, Asia, and beyond, carried by the unity of the supercontinent. This gave dinosaurs a global stage on which to evolve and diversify, ensuring that when competition faded, they were ready to dominate. As we pause at this moment in Earth's history, reflect on the resilience of life. From near total annihilation, new creatures emerged. From small, lightly built reptiles came the dynasty that would rule for over 160 million years. The dawn of dinosaurs on Pangea reminds us that even from devastation, new beginnings are always possible. In the next section, we will explore the ecosystems of Triassic Pangea in detail: the deserts, forests, and rivers where dinosaurs, reptiles, amphibians, and plants coexisted. Weaving together the fabric of a renewed world,